Good morning. First of all, I would like to thank Redglue for the opportunity that you gave us. I know it's not an easy job to have a couple of young minds here together and having this training for 5 solid days. So it's my colleague and I and every other person. We're very appreciative of this effort, and we want to give you a thumbs up. Thank you. So, going to our presentation, like we already know, we are working with a credit fraud detection uh, problem. So basically, that's the data set that we're given. So let's just quickly go into uh, what our project is. It was done by myself, Sadiq, and Luis. So. Yeah, we did a couple of things in Python. We imported a lot of libraries, especially in scikit-learn, matplotlib, numpy, and yeah, a couple of implementations that we have in Python were imported just so when we use them, so that we know that these are the libraries that we used. So this was the CSV that we were given. This is the sample data that we had. It's a credit card data set, but the problem with this data set is a lot of the features we have there were anonymized. So because for financial reasons, we don't need to know all the columns, but we need to see the meanings that some of those columns portray. So they were quite labeled in a way we can understand. The only thing that we know from this data set that we can tell from looking at it is the time and the amount column. So, and that was on the first and the second to the last columns. So looking at the data that we have, if we have a simple description of the data, we have the count, the mean, standard deviation, just to have an idea of what the data is, what's in the data, what sense can we make from a glance. And one of the major things that we did was to look at the predictors, what we want to predict, which is the class. So the class is either 0 or 1. 0, which means it's not a fraud, and 1 means that it's a fraud, that the record line is a fraud. So what this set means that we need to see how many, if we have a new data set, how do we classify how do we have a model that if you have a new data set and you push that data set into the model, how does the model behave and classify this new data as either a fraud or non-fraud using the examples that we have. And for that reason, we need to do some work on the existing data set that we had. So if we look at the data set so well, we'll see that we had quite some distribution, which is like the ones that are not fraud. The data set that we have that is not fraud is about 99.83% of the data set. And the ones that are fraud is 0.17. By default, whatever data that you push in, there is a 99.83% chance that the data is going to be classified as non-fraud. So, looking at this, we don't have enough example for data to learn and learn from, because you really learn from mistakes. Even in real world, you learn from mistakes. You have self-driving cars. There will be mistakes. There will be people there will be barricades. There will be a lot of training sets just to navigate and meander through this through these obstacles, so to say, or through these objects, just so that in future driving sessions you would have to go without having accidents. So basically, that's what we want to achieve with this. And so if we have a very small number of fraud cases, which is actually what the data set needs to learn from, we are not going to have a very good classifier, which means whatever data we throw into our data set, into our model, is going to be classified as non-fraud. In a nutshell, I've kind of explained what overfitting kind of means. So I mean, it's obvious that the zeros are so much more than one. We looked at the distribution as well because we're looking at what data are we working with. We have data from so many range from, let's look again, the minimum and the maximum of the time. So the count is this, which is the total number of the entire data set. But the minimum is 0 for the time. And then we have a maximum of 172,792, which is like so big of an interval. The same thing with the amount as well. We have a minimum of 250. Yeah, we have a minimum of 0 and a maximum of 25. That's not only the problem. If you look at everything that is in between, which is the interquartile range, which is 25%, 50%, 75, it doesn't even make sense to retain these values and then having a maximum of 256. So we had to do something with the data, and that takes me to where we worked on the data. I mean, we can't work with the data like this. It's so sparse. So we need to kind of scale the data so that we work with a balanced data set. And so one of the techniques, some of the things that we did was to split the data into sets. So we have a training set and we have a test set. We stick to, I mean, as a matter of uniformity, we stick to a random fit of 42 so that everybody can be on the same page. And the test size was 0.2, which means that our training set will be 80% of the entire data set, and the test sets will be 20% of the entire data set. So because we want to keep track of our data, so because our intention was to implement several stages of data pre-processing and data cleansing and even model optimization and all that. For that reason, at each stage of all this processing, we need to identify the data we're working with, because at some point we'll need to work with the raw data as it is. At some point we need to work with the scaled data. At some point we'll need to work with some other data that we have processed in the middle of the algorithm. So we kind of made this assignment. So we have X trained unscaled and X. I mean, we appended unscaled. So we know that this data is what we have. So it's still the data that we had from the very beginning. It's just that we've splitted this into train and test. I think it's the same with this one as well. It's the same with this as well. And yeah, so we want to have an idea of what our data looks like. I think it's better seen on a larger screen. So we want to have an idea of what our data looks like and how our features correlate, even though we don't really know the meaning of these features, but it would be nice to know what this represents. I mean, just an example, looking at the blacks, you'd see that I'm making an example here. V16 and V5 have a very strong negative correlation. That means if you're looking at probably combining, looking at features that have a combined effect on the class, we can definitely look at these two classes and say that, okay, with the combination of these two, they had a very strong, maybe not individually, have an effect on the class. As we can see, V16 and the class itself. Yeah, well, yeah. I mean, we can see that. I mean, there's a strong negative correlation between V16 and the class, and also there's a strong negative correlation between V16 and V5, which means, I mean, at some point where we get to feature engineering, we can see how not only using a single feature, but I mean combining these features together, we can actually improve the features that I want to do, because these are 30 uh, features. Some might not really be needed. We would see that when we used the decision tree classifier, we would realize that some of those features might not really be needed. But um, so I mean, just to retain the real ones. We also did some
Other one.
what?
Oh, you want to show the?
Yeah.
Okay.
So we also did some
Box then.
box plot just to see where we have a lot of features. So we tested it on V1 to V30 just to have an idea of what this V's could mean. And we tried to see, some had some outliers, and yeah, but so much couldn't be said about the variables, except the ones that are very, very obvious. But
Sorry, just a question regarding the correlation matrix. There was a balanced data, right? The
yes,
correlation.
yes, the pure data.
All the data?
Yes.
Sure. Okay.
All the data. We'll get to the one where we did the balanced one.
Okay.
So yeah, that's the box plot. So going back to, so yeah, we had a function that evaluates our model just to give us an idea of how our model is performed at a glance. I mean, by just running the function, we have an idea of and it helped because we used some classification techniques on the raw data. So we used some classification techniques on the raw data to see how well our classifier behaves. The first one was random forest, and it wasn't so. Sorry, it takes a. Do I have to run this?
No, if you already have the results, you can just show them, because if you are going to train the
Yes,
now,
that will take a while.
it takes some time.
Okay.
If the results are already shown, you can do it.
Oh. We made some last minute.
It's already done.
Okay, so yeah, so we had random first, and we. So, I mean, our area under the curve, which is a good measure of how our classifier behaves. We had a score of 0.88, which is not so bad. We had, if you look at this truth table, we had about a good number that is classified as that's fraud. That is not fraud, and it is actually not fraud. And we have the one that I classified 74 that I classified as fraud, which is actually fraud. And so these ones were misclassifications. The number is quite little, so I'll give you some credit, 0.88. Then we have a K nearest neighbor. It's predicted so badly, especially for for the 93%, 93 cases where it said it is not fraud and they were actually fraud. I mean, if we have a data set of about 400 and something, almost 500, and you classify them and you have about 93, that's about 1/4, 1/5 of. So it's behaved so badly. And then we had decision trees, which kind of worked a little bit more better. We had 0.91 area under the curve, and we also used some other classifiers, which is MLP. It didn't give us so much, especially I didn't like this one so much because there were some cases where it couldn't even predict true negative fraud cases. So it was a no-no. And then we had a Gaussian, which is not so bad, with 0.81. So after looking at these classifiers on our raw data, we felt that we need to work more. We felt that we need to work more on the data and maybe transform and scale our data. So that was the reason for us to go through this. So we scaled the test data separately, and we scaled the train data separately, scaled the test data separately. We looked at how it looks after. So we had a new column which is scaled amount and scale time. Then we had to put it to test, and so this is the new correlation matrix. I think I'll just have to rush through this. Now, we had a distribution of our new columns, the time column and the. So instead of working with the raw column with the large distribution, we're working with a more scaled data now, and we hope to test how this behaves with the classifiers that we've done already. Now, we're taking it a step further. Not only scaling the data, we're also balancing the data to see. Even in the scaled data, we still have a disparity on the percentages of fraud and non-fraud, which is obvious. So we had to kind of balance it. We tried to do the oversampling. So which kinds of add more data to the existing non-fraud data, so that we can have a balanced set for the two of them. And we tried some cross-validation. We were going to implement some other, retrain this on the classifiers that we had, but I think we were a little bit.
Yeah, we were tied with the time.
Okay.
In the end, what was your best classifier?
It was definitely the
Random forest.
No, decision trees, because we had about 91
Before and after the slot, the oversample?
We didn't end up all that.
Yeah, but
We
on the
were
test,
making them.
So you didn't use the decision tree with balanced data?
We used the point was that we were making like different files and different approaches.
So we didn't
and
add
we
it
were
in our
collect-
combined work.
Yeah, we were
Okay.
combining all to the presentation, but we didn't have enough time for combination.
Yeah, you can work at home after the workshop.
And that's it.
So can you show me again the decision tree?
For the decision tree, this was the best. Random forest.
Did you optimize the actual parameters?
We also did that, but it's not on the presentation.
Okay.
But
It's
with that,
91, right?
João know that I had
Yeah, I
an
saw
issue
it.
with that. That when I was optimizing the parameters for decision trees, what happened was that I get like a really good result, like 100%. Not 100. No. It was really
Good result.
good accuracy. The point was because with the optimization, he was always classifying it non-fraud.
Not fraud.
And
Yeah.
as the class is so low, the fraud, that was we understood that it was an error, so we were not getting good.
Yeah, but
good
this
results.
is a common problem on fraud.
Exactly. Well, it happens in all when you get this discrepancy. I don't know how
Yeah,
to say that.
yeah.
Like a class that is huge and other
And
one
the
that
other
is
is
small.
very small. Yeah.
So replying
But
to
it's
your
supposed to
answer-
be like that in fraud, otherwise
Yeah.
we had a lot of frauds and
But
that
answering
will
to your
be
question, we
very
did a lot more work, but we didn't have time to
Yeah,
combine it.
I know what you did.